Welcome to Mr. Honeycutt's math class. We're going to look at x to the evens and x to the odd functions graphically, numerically, and algebraically, and connect between those. So we're going to start with x squared. Okay, it's a simple quadratic. Let's look at the numerical to see kind of why it has the shape it does. So when I input the -3, a -3 squared is 9 because a negative times a negative is a positive. And plotting that point, I've got -3, 9. So that's going to be right there. The next input value is -2. -2 squared is a -2 times a -2. That's a +4. Inputting that value puts it right there. A -1 squared is a +1. So -1 squared is 1. 0 squared is just 0. So that's the point, 0, 0. 1 squared is just 1. And 2 squared is +4. And 3 squared is +9. So connecting those dots is what gives us the shape of the parabola. And it's kind of an ugly parabola, but you get the idea. I want you to notice, we got an axis of symmetry here, and it's symmetric because a negative times a negative is a positive. So these values are the same as their counterparts. The 9 goes with the 9, the 4 goes with the 4, the 1 with the 1, okay? Because the negative times a negative is a positive. So that's why that's doing what it's doing. That's why it's symmetric the way it is, why all quadratics are symmetric. So just looking briefly, notice the domain is all reals. The range in this case is from 0 to infinity. It is decreasing from -infinity to 0. It has a minimum here, so there's a min at x equals 0. Then it's increasing from 0 to infinity. The end behaviors are both positive infinity and positive infinity. So the left end behavior, the left end is positive infinity. As it's going this way, it's going to positive infinity. And as it's going this way, it's going to positive infinity. What you're going to see on the cortex, so that's to the 4th power, we're going to have very similar things. So this is -2 to the 4th. So that's a negative times a negative times a negative times a negative. That's going to end up being positive. And 2 to the 4th is 16. So graphing that, that's going to be -2 to the 16th. Now I've got -1 to the 4th. Again, any negative to an even power is going to be positive. So that's just going to be +1. All right. 0 to the 4th power is still 0. 1 to the 4th is still 1. And 2 to the 4th is 16. Connecting those dots, it's going to look like that. And again, what's the domain? Well, the domain is going to be all reals. The range is, again, going to be 0 to infinity. It's going to be decreasing from -infinity to 0. That's going to have a min at x equals 0. And it's increasing from 0 to infinity. And the end behaviors are positive infinity on the left and positive infinity on the right. Hey, look at that. That's identical to the x squared. It's almost as if these x to even powered functions basically act very, very similarly to each other. Why, yes, they do. All right, and then if you go for here, so this x to the even, if you graph any of these, it's going to have this sort of basic shape, this U shape, okay? All right, regardless of what it is. If it's to an even power, any even power, it's going to have some sort of U shape, or positive even powers. All right, so then, and then the domain is going to be all reals. The range of just the basic polynomial, it's going to be from 0 to infinity. It's going to be decreasing from -infinity to 0. And it's going to have a minimum at x equals 0. And then it's going to be increasing from 0 to infinity. And the left end behavior are going to be positive. It's going to come from infinity and go back to infinity. All right, and that's the basic shape on even degree polynomials. So that's why if the leading exponent, the degree of a polynomial, it's going to take the shape of this. All right. Now, looking at odd degree polynomials, let's see how this works. Let's plot this first point on x to the third. So it's a -2, okay, but it's -8. So it's down here, right? And then if I do -1 cubed, it's going to be -1 again, because a negative times a negative times a negative is still negative. 3 negatives, an odd number of negatives makes a negative, all right? And then 0 cubed is still 0. 1 cubed is just 1. And then 2 cubed is 8. Sketching this graph, it's going to look something like this. And it's important to note that it flattens out right here at 0. That's the difference between this function and tangent, which it can look very similar to. Tangent has a slope of 1. This one has a slope of 0. And if you think about it, that makes sense. Think about right here, we'd be plugging in a value of about 1/10. Right? Well, 1/10 cubed is going to be 1/1000th, which is close to 0. So it's actually going to, the smaller the fractions are, the flatter it's going to be. So as it gets closer to 0, it's going to make the line even flatter. So looking at domain and range, again, the domain is all reals. And then, hey, look at the range. The range is all reals. Okay? And in this case, it's actually never decreasing. It doesn't have extrema, but it is increasing for all reals. Its in behaviors, the left in behavior is -infinity, and the right in behavior is positive infinity. So notice, and the reason why, looking at the ends, the reason why is a negative to an odd power is still negative. That's why its left behavior in behavior is it's going to -infinity. But a positive number to an odd power is still positive. So that's why it looks different than the x squared, because of how many negative signs there are basically being multiplied by each other. If there's an even number of negatives being multiplied together, it makes a positive number, because a negative times a negative is a positive. But if there's an odd number of negatives, it's going to make a negative. So the x to the fifth didn't actually, I couldn't fit a graph on here. So, but let's look at what that'd be. That'd be -2 to the fifth, which would be a -32, and -1 to the fifth would be -1, 0 to the fifth would be 0, 1 to the fifth would be 1, and 2 to the fifth would be 32. So if I were to sketch sort of a graph, all right, and this was my -1, -2, 1, and 2, and I got a 0, and then up here is 32. Down here is -32. This is obviously not to scale, but it's going to look something. I should probably do like a 1. Yeah, 1, 1, or that's a negative. That's 1. There, there, there. It's going to have basically the same shape, right? And again, the domain is all reals. The range is all reals. There's no decreasing. It's only increasing. The left in behavior is -infinity. And the right in behavior is positive infinity. And that's what an odd function looks like. It's going to, regardless of what they are, it's going to have this same sort of basic shape. It might have, like, it might be higher sloped, so it might look something like this, where it almost looks vertical for like an x to the 9th or something like that, or even more, but it's still going to have that basic shape of of an x to the odd function does. So, and again, the domain and the range is going to be all reals. It's going to be increasing for all reals, and then the left in behavior is going to be -infinity, and the right in behavior is going to be positive infinity. Remember, that's why it's easy to determine the in behavior just from looking at the degree of the polynomial and of the leading polynomial, the highest degree term, the highest exponent term in a polynomial, and then using that and the sign of the coefficient in front to figure out the in behaviors. So that was an x to the even, an x squared, an x to the even, an x cubed, and an x to the odd. Notice the connections between the shapes. Notice why the shapes have the shapes they do. It's because of the negative sign rules.